Hello everyone. Welcome to part 2 of Introduction to Protective Device Coordination 2023. Today we're focusing on fuses and how they fit into the equation. My name is Jim Chastain. I'm an applications engineer here at EasyPower, and we welcome everyone in attendance today. Just a couple quick notes. The session is being recorded, and we will send out a notice when the video is uploaded to our website. Everyone in attendance will receive a certificate of attendance that folks use to support their EU requirements. And you're welcome to enter questions at any time using the question frame and the GoToWebinar control block. And as we're in the habit of doing, we'd like to start with a poll question just to get some feedback from the audience to make sure we're all on the same sheet. No obligation or no liability. The first question is, what type of protective devices do you use most often? Again, if you would just kind of indicate your situation or your preference. No obligation or liability. Just helps me understand kind of where the audience is coming from and where we may need to spend a little bit more time as far as the presentation. Okay, looks like we have a quorum. Thank you. Here's how folks have weighed in. And it looks like breakers are a clear winner as far as the popularity contest. Good. Interesting, actually. Very good. So the second question is, when using fuses, what part of the solution causes the most difficulty? And this kind of portends where we're going to be spending time talking about fuses in the presentation. Because all of these, as I'm sure we're going to agree, all of these come into play when you're choosing the protective device and trying to simplify the scheme that you're trying to utilize. And frankly, that's balanced against the cost and complexity. So hopefully we can shed a light on some of that decision making. All right, looks like we have a quorum. Thank you for participating. Here's how folks have weighed in. And it looks like we're all on the same page as far as where we want to spend time in the presentation. Good. Excellent. Thank you for joining us today. If you didn't attend last week, I'd encourage you to go back and review the video. We're going to repeat some of the basic concepts, but I spent a lot of time getting into the deep weeds about TCC curves, and I can't overemphasize how important an understanding of what that very rich tool lends as far as doing system analysis. But today we'll be focusing on fuse protection and the NEC guidance as far as the changes in the National Electrical Code. So we're going to be talking a little bit more about TCC curves, rating, coordination, and then the guidance that the National Electrical Code requires. Just in review, prevention of damage, fire, human risk, and supported by legal requirements is what pushes or enforces the need for protection of the system. Selective coordination is the procedure that we implement to reduce the amount of de-energization of the system unnecessarily when we have a fault detected, especially on a remote load. So, interesting enough, frequently, selective coordination will result in higher arcflash incident energy, because if you think about it, what we're doing is slowing down the protective devices at the higher part of the system, the upscale or upper end of the system, versus the protective devices nearest to the load. And by doing that, we're going to allow longer trip times for what's primarily the arc flash protection for, in some cases, the higher energy part of the system. So the twin goals of maximizing protection and maximizing coordination often conflict. And the protection engineer must strike a balance, or at least a justifiable resolution in making these decisions. Now, when we're comparing fuses with breakers, generally fuses will be a lower cost, and they do have the advantage of providing, in most cases, a current limiting result, which means once they're in a current limiting fault or current fault, they will clear in a half cycle as long as they're in the limiting band. We'll talk a little bit about what that means. In general, fuses offer the highest interrupt rating. Unfortunately, they're a one-time device, so you need to have fuses of the proper size in spares. They are very useful in doing arc flash reduction. They do have the downside, or the risk of single phasing if only one phase senses a fault or the fuse clears in one phase quicker than the other two. And then probably less focused on, but certainly is a concern, is the risk of replacement with the wrong fuse, because inadvertently, by putting in a larger fuse than what the design required, you could actually reduce the lifetime of a transformer or equipment that was supported by that designed-in part, or increase the arc flash hazard downstream of the fuse, all of which is a concern when you're doing a study. In fact, that's one of the reasons when you do an update on arc flash data collection, you want to make sure you're checking all the protective devices, and in the case of fuses, making sure all three are the same manufacturer and part number and size. Just an aside. According to NEC 110.9, the equipment intended to interrupt current at fault levels shall have an interrupt rating at the nominal circuit voltage at least equal to the current that's available at the terminals of the equipment. So this is, again, the requirement to have proper rating based upon the location in the system. Fuses generally have an extremely high interrupt rating, and if selected properly, several fuse types will be acceptable in a tested series combination. That's a term that we're going to be bringing up several times, the fact that testing, when we're talking about combining for series rating or for arc flash from different manufacturers or even the same manufacturer, the result needs to be tested, or the combination needs to be tested before you can accept the simulated result. Hopefully I'll explain that as we get into this. Okay, so the rating of any panel, assembly, or bus is the combination of all the included devices, or the constituent parts, and it's the rating is limited by the lowest rated part in that particular assembly. So the short circuit resistance is listed on the data sheet for each of the components, and then tested by a manufacturer lab for the panel itself, for the buswork itself. Equipment duty of breakers and fuses is a rating that needs to be adjusted based upon the X over R difference as installed and tested by the manufacturer compared to the X over R of the installation where the part is being used. Now in EasyPower, that's called smart duty, And what it means is that the max fault can be less contribution from the feeder adjusted by the X over R. In other words, and the term underrated or overdutied is synonymous. So let me see if I can make an illustration of this. So I'm going to open up an example that I've saved here. And the point being, the same fuse used in different, the same protective device used in different parts of the system could have different results. So here we have a fuse protecting or upstream of some breakers. And if we go into short circuit, EasyPower has a nice function in short circuit. We're going to look at the current, half cycle current, and fault all the buses. And what that shows us, we're looking at the A phase, but if switchgear 4 bus faults, it'll be 21,750 amps coming from upstream. Because there's significant motor loads downstream, there'll be 2,000 amps, 1,600 amps, and 1,400 amps going through these breakers to give us a total available fault current of close to 27,000 amps. Now, not every breaker will feel that the effect of that current, and so it needs to be rated specifically for 25,000 amps is what we've got. Let's go in and check. So if I look at the breaker for, I think they're all three the same. So based upon the selection of this breaker, we can see it's rated. Now I haven't auto-calculated because I'm kind of salting the results. But in this case, let's assume that the rating for the breaker is 25,000 amps. And my fault current is 26,000. So if I go back to short circuit, look at, and let's just fault this one bus. And then look at equipment duty, which is this little quotation bubble on the second row. I see it's flagged red with a bunch of different numbers. Now what these represent are a threshold for rating of that individual part based upon the manufacturer's data sheet and the this compensation between what the manufacturer tested X over R wise and what EasyPower is testing or simulating in the application. The numbers with the negative sign mean they're still compliant, but they're within the 10% threshold that we've set. The one with a positive number means that it's over dutied and is exceeding its compliant rating by 1%. So for the same breaker, because we have different current affecting that particular breaker and the X over R is being compensated for, we have a fuse that's compliant and two breakers that are non-compliant or over-dutied. And that result will show up in my, I've got it check marks, my equipment duty report. And so this shows us for each of the devices, the fuse is not within its 10% bandwidth, but each of the breakers are, and in two cases we have clear violations and then two warnings. Mike's asking, can we actively auto-calculate as a default? Okay, I think you're talking about my salting the equation. So let's go back. I think the question he's asking is correct, and that is, if we've properly set these parts up for auto calculation, will it work? And the answer is yes. So if I auto calculate, I see that device library tells me this part's actually rated for 42,000 amps. So I'm again, I kind of salted this example to show off the advantage. Same is true for this one. Let's go ahead and auto-calculate to make sure I'm using the right data sheet. Short circuit, auto-calculate. Again, it's 42,000 amps. And by doing that, again, what I'm trying to show is that this, if I properly set the tool up, the one line up, I don't have to worry about this. But if I have an actual miscoordination or misrating on my system, the tool will detect it. So now I go back to short circuit, fault the bus, look at equipment duty, and I see everything is good because we're way clear of the 26,000 amps, except for the bus itself. If I go back and look at equipment duty, now I see all my breakers are good, but the rating that I've entered for the switchgear is within 3% or 4% of its rating. Good question. Ovid is saying, why is the half cycle short used for breakers? This is a requirement from ANSI for testing low voltage power circuit breakers. And so there's a specific, the maximum current is going to be during the first half cycle of the fault. And so that's why we need to pay attention to the X over R that the system was tested and the X over R in my application. It's different for high voltage and medium voltage breakers, and it seems like we'll touch on that as I get farther into this. So anyway, now, got another good point. I think I have let me get back to that's an excellent question, and there's more to it. And if you have access to the EasyPower help system, you can see the explanations for some of this. So I'm going to jump back into my PowerPoint and see if I can find the slide that talks about it. Okay, so the point that we're making is that the tool automatically takes into account this X over R difference between when the part was tested in the factory and when it's plugged into our system as an actual application. So this is what I just showed, that the equipment duty can be shown in short circuit reports. The most accurate are the equipment duty reports, but it includes the function of smart duty, which is calculating the compensation for the X over R and the reverse current that's not felt by other devices. ANSI short circuit references are in the device in the help system in EasyPower, and you can find it if you go into the help system and look for ANSI short circuit reference, short circuit options, and then the text output tab. And this explains exactly what I was kind of fumbling around with as far as the test procedure that the factory uses and the fact that EasyPower reverse engineers that result. Good question. So the fuse manufacturers, Chuck's asking, so the fuse manufacturers promote the up, over, and down method to reduce available fault current using their fuses, but we cannot use this according to NEC if you're, am I thinking correct? The answer is yes, and I'll touch on that a little bit later. And where is the up, over, down useful? Chuck, you're about 2 slides ahead of me, so hang on to that. And then Robert's asking, can this use be tested for motors to see if they meet the MCC, so the SCC? The answer is yes. That's a good question too. It depends with, let's go back. I've not answered that question before. So before I do that, let's look at that. We're talking about a different test system. Go to short circuit, fault all the buses. Look at equipment duty. Now my short circuit report, if I come up here and say I want equipment duty and I want to show all devices, then when I look at the report, it should show this bus, which is the motor connection. So let's see what it says about the motor, M1. So the answer is no, as far as a standalone motor. If I had a protective device like a fuse disconnect or a breaker down at that bus, I could see what the current was, but it wouldn't tell me whether the motor was being exceeded or not. Can fuses be loaded to 100% rating? Hang on. Again, you guys are one step ahead of me. So what we're talking about is interrupt rating. So fuses are usually the highest rated element in the system. And a fully rated system means that all the protective devices can safely interrupt the available current. For instance, in this example here, I have a short circuit available current of just under 32,000 amps. But my protective devices are all rated for 65,000 amps. So we refer to this situation or this combination as a fully rated system. Now, EasyPower has in the default mode, it uses the database ratings from the device library. And we'll touch on that briefly if you don't know where that can be. But a fully rated system will be seen where selective coordination is desired or required. In other words, we can't get coordinated. If we don't have a fully rated system, we can't really guarantee coordination. Now, series rating is, in effect, if I use a higher rated upstream device to protect lower rated downstream elements. So in this case, we have the short circuit available current on this bus of just under 32,000 amps. Each of these breakers is only rated for 10,000 interrupt rate amps. But if we use a properly selected overcurrent protector device that exceeds this rating, exceeds this current, then we can have what's called series rating. But it needs to be tested with the downstream device before we can guarantee that it works. And normally the tested pair includes a circuit breaker downstream. Now I keep referring to the fact that this is tested. Usually the series rating for fuses and breakers, you can't verify it from the data sheets. It needs to be a tested combination. The point is both devices are likely to clear the available current, and then both devices are likely to open, especially if this is a fuse, at that 31,000 interrupt rating, or 31,000 amp fault. Now, EasyPower does not provide series rating for fuses, so these must be manually selected, but we do provide series rating for breakers, provided the manufacturer's test results are supported. And I'll get back to that in a minute. So selective coordination, as we explained last week, is the analyzed or simulated results to ensure that the breaker closest to the fault, in this case, we have a fault on this bus on the left, and all three protective devices in series could sense that fault current, but we want to make sure this breaker trips first, and the tool to do that is called the TCC curves. So we'll jump into TCC curves in a minute. Low voltage fuses, the common types, most of which are current limiting, more so in today's market. And they have certain certain features to allow misapplication or misplacement, misreplacement of parts that are not compatible with the other parts. So the fuse will not always be current limiting. A typical low voltage fuse curve looks something like this. It's inverse. It's an inverse curve, and it can either be designated by its minimum melt, or its maximum clearing, or the average melt. And where there's, in this case, I think this is a minimum melt curve, the width of the curve is determined by the manufacturer, and it's usually plus or minus 5% of the average melt. So EasyPower, once we're given the average melt, will give you a band that includes the additional time. For current limiting fuses, using a ratio of 2 to 1, as you go upstream in your system, will, according to the manufacturer, allow coordination. So it's important to note that EasyPower device library is based upon manufacturer's data. We don't make up any data that the manufacturer doesn't provide for us. So when you're providing fusers or using fuses for transformer protection in the primary side, you need to be able to ride through inrush specifically. So as we discussed last week, these two parallel lines represent the transformer damage curves. The dotted line is a 100% damage curve. The solid line is a 58% single line to ground for primary protection. So any protective device we have, we want to make sure we stay to the left of one or both of these curves. The inrush is this little dot down here below it, and this is usually assumed to be 8 to 10 times the full load current of the transformer, and somewhere around the 0.1 second time. And so that's the coordinates of this particular dot. So any primary protection we have in this system needs to be to the right of the inrush. Anything to the left, potentially it could be tripping as you turn or energize the breaker for the first time. And all this is based upon the self-cool rating. And again, EasyPower handles all the math in the calculations. According to the National Electrical Code, there's tables that give us protective percentages compared to full load current. And so this is the low voltage where everything is less than 1,000 volts, and primary protection and secondary protection on a transformer of less than 1,000 volts and greater than or less than 9 amps. Most of the time, this is not the big problem area. It is, I think, useful to look at the table notes for that table we just described, because this is going to be the guidance for current and recommendations for fuses or circuit breakers. When you talk about non-adjustable, these are the molded case circuit breakers that should be considered when we're trying to protect smaller transformers. Ovid is saying, is it true that some small transformers can have an inrush of 12 to 20 times? Anything is possible. I'm not a transformer expert. That's something that you can go to. You should have as far as the data sheet from the manufacturer. And while I have one open, let me show you what we're talking about. If I go to database edit, I look at the transformer dialog box, I have the ability to, on my TCC curve, to change the magnetized inrush. So based upon full load current, if I wanted to say 12 to 20, I could change this number. And based upon the number of cycles I wanted to be conservative, I might increase this to 8 or 10. So again, based upon the manufacturer, these are typical numbers for larger transformers. By all means, use information that you get from the manufacturer. And if we didn't attend last week, I think I went through all this information on transformers in fairly good order. Okay, for transformers that are more in the power system range, this is the table 430-3A, where primary systems over 1,000 volts and secondary systems over 1,000 and less than 1,000. And it's segregated by the impedance ratio, less than or equal to 6% and greater. And what this tells us, for primary protection, we can use a breaker that's rated up to 6 times the full load current rating for the primary protection if we're using a breaker. But if we're using a fuse, we really want to be, we want to limit that to 3 times, or 300% of full load. So this is a good reference point, and if you're doing new designs, this is something you should pay copious attention to. I wanted to point out just real briefly, and regarding transformers, strongly recommend when you're doing data collection to utilize a digital camera to take a picture of the nameplate, especially in transformers, because these have all the data on them, and sometimes your spreadsheet or whatever form you're using to collect the data may not have at least the need based upon your focus for the study, but having a digital image, you'll have all the data that can be useful if you need to expand the application. So for instance, the kVA rating, the primary voltage, secondary voltage, the impedance ratio 5.55, the type is oil filled, the heat rise and 65 degrees C, and then the full load current is 43.78 amps for this 13.2 kV, excuse me, 13.2 kVA. So having this digital image can be associated with the project in EasyPower, and we're going to walk through kind of selecting a fuse for this particular transformer, or a transformer. So, I'm going the wrong way. So we're looking at less than 6% impedance ratio. We're using a fuse. The primary is over 1,000, and the secondary is over under 1,000. So the maximum is 3 times the full load current rating, and 1.25, 125% of the secondary rating. So if we do a little math, the full load current for the primary is 43.74 amps. Full load current for the secondary is 1202. And for primary fuse protection, we can go up to 3 times that current, which would be a maximum of 131. Now, you don't have to go that high, but that's the maximum that you don't want to exceed. And then for secondary, it'd be 1503. So what I want to do is show on my little fuse protection for transformers where all this stuff plays into effect, comes into effect. So let's close this puppy out. Okay, so I'm just going to wing it here on entering the data for my fuse. Let's say on the primary side, I've picked out an AB chance. I like to go with fuse links, Model T, and a full load current of 43 amps would give me a max rating of 300%. So 131 is 300. So I'm going to start off with 100 because the next one up is 140. And once I go to short circuit, now in this particular case, this is a fuse link and there's no coverage or fuse holder. So the interrupt rating doesn't apply. This is just a piece of copper strung across the switch. And then for my secondary protection, I want to use a busman. And again, I've not looked at I highly recommend talking to the manufacturer and getting a recommendation based upon the size of the transformer and the loading that you're expecting. But failing that, I'm winging it and use my selection with the TCC curves, or making my adjustment. So 125 is 1500 amps. So let's go to short circuit. And again, the X over R and the interrupt rating for a fuse with the holder on it. Okay, so let's see how this works out. I've got my utility data. I go to coordination, plot the curves. Now for starters, let's take off the secondary protection. We'll talk about that in a minute. Just select it and delete it. And expand my display a little bit. Now, what we talked about for the transformer, here's a tick mark for full load current. And if I look down at the coordinates on the bottom of the screen, as I hover over the full load current, it shows 1250. Well, if we're talking about the primary side, why is it showing me 1250? Well, the tool automatically picks out the lowest voltage side of the transformer and rates the TCC plot on that. If I want to display what the primary, with reference to the primary voltage, I right click on the primary bus, set it as a reference for TCC scaling, and the tool moves it over. So now if you watch my coordinates down here on the bottom of the screen, and I hover over the tick mark, it shows 42 amps that we calculated for full load current. Now, this dotted line is my 100% never exceed. I'm going to move the fuse out of the way for a second. I want to never exceed this 100% point, and I don't really want to exceed my frequent fault curve, which is what this reduced current segment is on the higher, reduced time segment on the higher current. Now, if I have primary protection and I have a hard fault or hard ground in my transformer, and I'm depending on this fuse to protect against a ground fault, then I need to be below this 58 derated curve because of the difference in phases. So in reality, I really want my fuse to be positioned more like this so that I have guaranteed protection for 100% duty, frequent fault, and I have protection for a single line to ground fault on the secondary. So if I hover over the fuse, you can see it's a size 30, that gives me protection for this 43 amp. So it's nowhere near the 300%, but it's full protection. Now, I haven't talked to the manufacturer, and I suspect that the manufacturer would tell me the size of the fuse that I would want to order. Okay, so Homer's asking when we talk in this case, because my reference point is 13.2 kV, which I'm showing down here at the bottom, then we are talking about primary current, my full load tick mark. If I come back and change my reference point to be the 480 side, right click, set as a reference point, now my tick mark is going to be on the secondary current. As I hover over it, it shows me the 1223 amp, which we calculated for the secondary. Now, if I want to look at the secondary protection, I want to turn my plot back on. Now I can see for secondary protection, I was talking 125%, and right here, I'm at 3,700, which is more than 125%. So I'm going to scoot it back. And if I want coordination, then I have to have it lower than the, now in this case, there's a little bit of, and what am I over here, and this shows me I'm at 986, which is way less than the 125%. If I wanted 100%, I'd be at 1200. So I'm going to move this to the right. And it's a case where I may want to accept miscoordination because I have the primary fuse lower because of this derated curve. So that would be something I would consider for coordinating both the secondary and the primary side for transformer protection. Okay. Now, when we talk about coordination, I mentioned that you want to have tested results from the manufacturer. So this is an excerpt from, seems like it's Busman. I forget where I copied this from, but gives me the amperage range, the UL class, little fuse, the little fuse part number, and then the load side versus the amperage range for the fuse on the line side. So for this particular type of fuse, I can have load side protection on, as long as I keep the ratio 2 to 1 as I go upstream to the next level of fuse protection. And so the purpose is to select the correct fuse amp ratio to maintain the selective coordinations, and these are expressed as line side to load side. So if we picked time-delayed fuse, and I have this shown in 03. So let's see what it looks like. So again, conversations with hardware manufacturers is invaluable. It's worthwhile making sure you get the right data to enter, but the TCC curve will tell the tale. And I want to show fuse coordination, same family. All right, so here we have Bussmann, Schaumet, and Cutler hammer. So if I go into coordination, let's see if I have them already done. So again, the ratio is 2 to 1 as I go to each level of my system. So here's 150 amp, 300 amp, and then 600 amp. And the manufacturer guarantees coordination as I go up that system. Jacobo saying the coordination with the fuse FS3 should require coordination of the damage curve of the equipment connected. The answer is yes. In fact, again, you're one slide ahead of me. What we're showing here, the red chair, is my motor damage curve, my motor full load starting curve. And if I were smart, I'd have the damage curve also included. Let's see if I can. So I'm going to plot the thermal damage curve for the motor. And so the answer is yes. I need to take in that damage curve as I'm selecting the downstream protection. Good question. Thank you guys for keeping an eye out for it. So the same thing is true for the, let's close this one. So that's Bussmann. Let's look at another one. Gould-Schaumet. And I'm not showing a load curve here, but you can see the 2 to 1 ratio for the foreseeable current range is, now these two tick marks over here on the right, which correspond to these tick marks to these curves, these are the thermal damage curves for the cables. And so at certain parts of the system, they need to be taken into account as I'm doing coordination. They can be the limiting factor, especially if my loads are not threatened. Okay. Now, this is where things get a little bit more complicated. Fuses coordinated with multi-case circuit breakers. They both have clearance, usually better than 1 cycle, guaranteed by the design. So the coordination has to be tested by the manufacturer. It's not always different. It's not always available for different manufacturers. If you have a test lab verify the testing or coordination, then that's something you can work with. I think the standards say as long as a professional engineer has verified. I don't know professional engineers of anyone that would go just on looking at the data to verify coordination. It has to be tested. Okay, so here again it's by manufacturer, but Eaton and Bussmann have provided a chart. This is for 240 volt thermomagnetic quick pick, and they show breaker family and then load side fuses that are guaranteed coordination if I stay within the range of min and max amp rating. So to try to show this off, I have a 240 Eaton Bussmann. And again, these are good examples for you to prove to yourself, because it's easy enough to kind of draw up a what if example using EasyPower. So here's a 240 Eaton Busman. What I want to show is coordination between the upstream breaker and the downstream fuse. So if we go into coordination, I did it. And again, like Jacobo mentioned, this is the damage curve for the motor. Here's the fuse, and here's the breaker. If I fault the downstream bus and expand this a little bit, you can see I have coordination for both elements guaranteed by design, guaranteed by test from the manufacturer. Okay, let's look at the other one. I think I have a 480 volt one. So the same type of information is available in this case. So you need to go to the manufacturer to get this data, and most are happy to help out because you'll be buying more parts from them. Having different manufacturers is not encouraged. Coordination didn't do it. I don't have my load curve on here, so we'll just imagine that there's so the fuse is okay, I don't get this one. Okay, I apologize for this because this is showing red, which tells me something's not right because it's not coordinating. Okay, let's table this because it's going to get too convoluted. Something's wrong when not coordinating the colors. Will smart PDC ever pick the best type of fuse to use for best selective coordination? No. Frank's asking, how smart is smart PDC? PDC is designed to go through the table of parts in a described or prescribed order as long as there's different values on the dial settings for adjustable devices. Since there's no fuse adjustment, the answer is smart PDC can't do that. What is available is if I hover over a fuse curve, I can left click and drag, and if there's another value, if you can see the insert, there's another value of fuse in the same family, then it will give me the ability to display it, but it won't come up with a different family in the Eaton data sheet. Okay. Now, NEC doesn't require selective coordination except on mission critical loads. And so they give us a list of this in the National Electrical Code, and these articles go through the different elements that were required and when they were added to the NEC. In 2018, I forget the version, the most recent version, 2021, there was a clarification of the requirement to do series coordination or selective coordination versus the normal source compared to the emergency source. And what they effectively say is that for the critical loads, when it's on the normal source, then D has to be coordinated with C, protective device has to be coordinated with B and A. And these can be the same value, they don't have to be different. Whereas with the emergency source, I have to have coordination all the way up to my source. And so it was NEC 2020. Part of the change involved focus on arcflash energy reduction. 24067 applies to fuses rated than 1200 amps or higher. The requirement originated in the 2017 version, but it didn't become effective until 2020 to give manufacturers opportunity to create products to solve the issue. So documentation has to demonstrate the method chosen to reduce clearing time, and it needs to be available to those authorized to design, install, operate, or inspect. The method to reduce the clearing time if fuses do not clear the arcing current within 70 milliseconds or less shall be set to operate at less than that available arcing current, and it needs to have performance testing. It only applies to fuses rated greater than 1200 amps or greater with a clearing time longer than 70 milliseconds, and an evaluation of the TCC curves is required. So EasyPower uses IEEE 1584 to calculate the reduced arcing current up to 106,000 kiloamps, and beyond 106,000, EasyPower can use roughly equations. So I put together this little chart to kind of illustrate what we're saying. Let me back out of this. And it starts to make sense once you look at the results, or at least for me. And this technique is that I use for this is I want 10B 1200 amp fuses. The point I was going to make is that you can't have isolated sources, which means I can't have different values of utilities connected together. And so I wanted different values, 30 kiloamp fault current, 37, 55, 85. I wanted them to be on the same one line. And so I put a virtual connection with an open switch so they never are connected, but I'm able to put on the same one line all these different utilities. And so what we're going to do is look at these results. Short circuit, fault all the buses, and arrange for arc flash. And what we see as I scroll over, for 70 milliseconds or less, I don't need to deal with it. For those greater than 70 milliseconds, then I need to provide a safety measure to protect people from the arc flash results. If I look at that, you can see I have 4.3 and 9.6 calories at the juncture where I'm having issues. So there's no further action required on those two, and I need to do something about the others. Now, those methods include differential relaying, you've got to have a choice. You can use differential relaying, energy reducing maintenance switching, energy reducing active arc flash mitigation, current limiting electronically activated fuses, or an improved equivalent means. And some of these parts on here are the reason they had to be manufactured by, or come up with, developed by the manufacturers, why there was a 3-year delay in implementation. So differential relaying, basically you have a differential relay sensing downstream faults and set up to realize when I have a fault greater than a certain level and open up the main, breaker, or fuse. Likewise, maintenance mode can be used on a local basis. It doesn't tell us what the maintenance mode needs to be, but just has the ability to adjust the trip settings when anybody's in the area. Now, some of the equipment that looks like this is available now and has data sheets on the market, and they can incorporate it, in a one-unit system, the ability to detect ground fault, short circuit overcurrent, and maintenance, have the ability to include maintenance mode. And so at EasyPower, they'd be simulated something like this. Another similar type of operation is a switchable fuse. And this is just an example. I'm not familiar with the details. I've just found the data sheet on the web, where Merson is provided inside of a medium voltage fuse, 2 fuse links, and with the ability to sense a downstream relay, an arc relay, the ability to trip open the normal connection and allow a current limiting fuse to be subjected to the fault current, and consequently you'll have a quicker reaction to an arc fault in the low voltage side than you would if you waited for low voltage arc flash protection. So what this looks like in an EasyPower implementation, and it's worth checking it out because it's not as costly as redesigning the whole system. But what it amounts to is I have the ability to call it a fuse group. It's simulated very similar to arc flash, where we have a relay that's tied to the arc sensing element, say a 751 or similar relay, can sense the triggering device for these fuses. And normally the fuse would go through, the high current would go through the main fuse and my high or low impedance link. And if I sensed an arc, it would open this switch and force the current to go through my current limiting fuse and thereby give me protection downstream. Simulating this, I set up the arc flash. It's just like I do in a differential or an arc sensing application. The reaction time of the fuse and the switch element. So now when I go into looking at arc on these, wherever my senses are placed, if I look at my arc results, I get less than 8 calories, which wouldn't be available if I just had breaker protection down below. Robert's saying, note, healthcare uses an FPA 99 that does not coordinate up to 1/10 of a second. Thanks, good to know. All right, so another similar technique or similar device that's been developed is quenching relays. And this operates very similarly in that they detect an arc on the switchgear and they automatically ground the bus, or whichever bus is being faulted, and it makes the upstream upstream protective devices trip instantaneously, which if they were fuses could be a half cycle result. And I get feedback that this can be a very cost efficient way of increasing arc flash protection. So again, it's if you're having to deal with this, it's a good idea to talk to the manufacturers that have a solution and can be retrofit in older systems. It's a fascinating topic, and I think it's not one size fits all, but it's worth researching the options. So we talked about system coordination with fuses, transformer protection, and the proper data entry will ensure that the TCCs will be accurate for load protection. And now arc energy reduction is required by the National Electrical Code for certain systems. So thanks for attending. Next week we'll do breakers and coordination, and be sure to check the website for other tutorials and video. Later this week, we actually have a Spanish language case study. If any of you are Spanish speaking, I invite you to attend that webinar as well. Have a good day. Austin, you're asking, should fuses be loaded at 100% rated or current or 80% of it? Well, it depends. That's a question for fuse manufacturers. I'm by no means a fuse expert. Depends on your system. In my mind, it depends on what your design ratio is and what your typical loads are versus full load. Good question. I'm not the guy to answer it though. Thanks everyone. Talk to you later.